We're going to do a quick review of area and volume. It's a huge topic on the AP exam, so we're just going to solidify it today. And then your worksheet will be a combination of these and some other, a wide variety of topics. Your ticket to getting the worksheet is showing me these notes. So the first thing is finding the area between two curves. And remember for that, again, we're going to go a little faster than normal. It's all about coloring, and it's all about coloring up these rectangles right here, and we make them infinitesimally thin, and we make an infinite amount of them, and we get what's called the definition of an integral, and we add these all up. And every rectangle's area is the product of its base, which is dx, times its height, and its height is going to be the top function minus the bottom function, in this case f of x minus g of x. So whenever you're asked to find the area, it's two-dimensional. There is no revolving, no third dimension, no pi, nothing weird. We just add up all those rectangles from intersection A, which if you're calculator active, you need to use calc intersect. If you're not calculator active, you set the functions f and g equal to each other and solve for x. So we're going to integrate from A to B the product of all the bases and the heights, which is going to be f of x minus g of x. And again, that will be the height of every rectangle. Dx is the base of every rectangle. So that's it for that one. Now, when they tilt it sometimes sideways, and that's what happens most of the time, but you need to be prepared also for a situation like this where we have what we call f of y and g of y. And if I were to color vertically with this one, I'd have to switch my top function and my bottom function at that point because they swap out. The line is on the top over here, whereas the curve is on the top over here. So, and over here it's the curve over the curve, and it just gets messy to do that one with dx. So usually this one would be done with what we call dy. We'd color horizontally up the y-axis. So we'd color like this and like this and like this with an infinite amount, and then been infinitesimally thin. And I'm going to color one in here and call this now dy because it's a tiny little change on the y-axis. So I'm still going to add those all up, but I'm going to be adding from here up to here. I'm going to be climbing up the y-axis. So instead of integrating from A to B along the x-axis, I'm actually going to be integrating from the y value there, which you could call f of A, right? F of B. Basically, just think you're going to be going from y to y though. And again, it's all about those rectangles that are made when I color, and I'm going to pull one of them off right here. And it's got a height of dy and a base or a length of that distance, and that's going to be right function minus left function. But my right function is going to be written as a function of y. So up here, we would write them as x comma y is a function of x, like maybe y was 2x plus 1, and we'd say x comma 2x plus 1. Well, over here, we are going to have our y being given, and our x will be in terms of y, so it's a little different. Sometimes those are given to you, sometimes you have to solve them. For example, if it was just linear, and y equaled 2x minus 1, I would say y plus 1 halves is the x-coordinate as a function of y. So we are going to do right function minus left function with respect to y. So everything's about y. I climb up the y-axis, and I have my x's solved in terms of y, and my differential is y. So then after we do area, we do volume. And we're going to first talk about when you revolve around either a vertical or horizontal axis. And that can be either the x or the y-axis or a vertical or horizontal line. So we're going to be whipping around some axis here. So let's go again. Draw a sketch. I'm going to make just a fake funky curve like this and another one like that. I'm going to call the blue one f of x, and I'm going to call the red one g of x. And I'm going to whip this thing around some axis. And let's suppose we're going to whip it around down here. Whoops, moved it a little bit. This axis down here. Now remember what these are all about. Now we're picturing 3 dimensions because we're going to take our representative rectangle. We're going to attach it with a little piece of invisible string here. We called it Dentafloss when we did it. And we're going to whip that whole figure around the axis. And what that means is each rectangle, when it whips around, remember, makes what we call either a disc if I have no dental floss, or if I butt up against the axis of rotation, or a washer if I have a gap like on this one. I have a gap between my axis and my rectangle. And these are all about adding up a bunch of cylinders. And cylinders formula is pi r squared h. But our h in this scenario is really this little distance right here, and we call that dx. Our r is from the axis to the outer edge is big R, and little r is the axis to the inner edge. So our formula becomes, we're going to integrate, we do pi times, and then again this would be a, which we need to calc intersect on if we have a calculator, or if we don't, we set the functions equal. We integrate from a to b, big R squared, minus little r squared, and this one would be a dx problem. But again, if I'm whipping it in the other direction around a vertical axis, then I'd have a dy problem, and it'd work similarly as the one above. So how do I get big R? I do top minus bottom function because I want the axis to the outer edge of the curve. So big R represents this whole distance right here. And to get the distance between two things, we always do the big, even if I was talking about numerically, what's the difference between -2 or the distance between -2 and 20? I do 20 minus -2, kind of top minus bottom. So on this one, I would do the top function, f of x, minus the bottom function, which suppose this was at y equaled, I don't know, -4. I would do minus -4, which would make it a +4. So big R is axis to the outer edge, and we always do top function minus bottom, whichever occurs. So keep in mind, if I had put my axis of rotation up here, then that becomes my top function. Maybe that's y equals 5, and so I do 5 minus, and again, the equation for the curve. So same thing. And this is axis to the inner edge. So it's like this. Inner edge. And it's still top minus bottom, and we'll do an example of that in a little bit. So last step was when we're doing the volume and we're building up off of a base. So really what you have is some region R, and you're going to consider R the bottom of some figure. So you have to picture dropping that y-axis flat, and R is laying on the floor. And we're going to build up or bake up off of it so that when we slice that loaf, so R is like the bottom of a loaf of bread, you're going to build up off of that base, and then you're going to cut it with a knife. And your cross sections make different geometric figures, and they'll tell you what the geometric figure is. So first of all, let's say R is equal to the base of the solid in this scenario. We still have intersections again that need to be calculated. We still look at this, but we're not whipping it around, and we are not finding, adding them up and finding the area, we're considering that the side length of whatever geometric figure they want me to build up off of there. So if I'm supposed to build up off of there with equilateral triangles, then that's the side of the equilateral triangle that's popping up and out of the screen. So the formulas for these all involve finding S, and it's what it's always been. It's top function minus bottom function, whatever they're called, be they f, g, e to the x, sine x squared, it doesn't matter. It's top function minus bottom function. So we start with the most basic, and that's when you build off of it and make square cross sections. So right here is that side, and you're popping up off of there with squares. Well, this is really your length times width times height. That's the volume of one of those slices, and we go from A to B. So that we just integrate side squared. If I'm doing an isosceles triangle with a leg across the base, so that S again would be, if you keep in mind your big picture up here, that S is what it is right here. It's stretching across of those two, and we're just using it as a side length of whatever geometric figure they're having us pop up out of the screen. An isosceles is a half of the square. So again, if we can find S, we can do all of these. If they give me an isosceles with the hypotenuse across the base, then that means these are the legs, and this right here is the side. So really what happens is I end up having, this isn't the greatest picture, but kind of chopping it into 4. That ends up being 1/4 side squared dx. Sometimes they'll have you build up off of that with semicircles. But again, this is still S, and the volume will always be, and our multiplier out front for that is pi/8, and it really is to your benefit to memorize those instead of trying to create them every time. So it'd be pi/8, and again, it'd be side squared dx. And then the one they rarely ask you, I've seen it asked maybe once, but you have to be prepared for it if they do, is if they build up off of it with equilateral triangles. Then the multiplier out front is √3 over 4, integral from A to B, side squared dx. Honestly, usually they have you do it with squares, sometimes isosceles, sometimes semis, but most common is the easiest one, which is the square. The most common errors for that, by the way, is kids putting pi's out front, and that kind of an issue. So that's it for the notes. One thing I do want to discuss is this is if you're building off and your cross sections are perpendicular to the x-axis. If we did it so we were perpendicular to the y-axis, so let's go up here, the theory behind it is identical. The only difference, oops, for some reason it's not erasing. The only difference is if I have to have my cross sections perpendicular to the y-axis, right? Then my side length is no longer top minus bottom. It's right minus left. And everything will be solved for x in terms of y. So this becomes, right here, a dy. All right, just so you, and again, my A to B would be going up the y-axis. So that's it for the notes. I'm going to do the examples. You know what? I'm just going to keep going. I'm going to do this all in one chunk here. So the examples on the next page, which just hope it won't take too long to upload. These are calculator active. You're going to need your calculator out. I will know if you truly watched the video because I'm going to leave the answers underbaked. So you're going to have to finish them up on your calculator. So this was last year's. The national averages, again, run between 2 and 4. This one, probably around, 3 is usually what we've been showing. So let's see how we're going to do on this one. I think I'm going to shrink this down a little bit so we can see it a little better. So just a sec, I'm going to shrink that down, move it on over here, and then create some workspace for myself. So I'm not doing all that scrolling. All right, so this was last year's. Let's see how it goes. It says f and g are the functions defined by these above, and I would go enter them into your calculator right now because it's calculator active. I'd put that one in y1. I'd go put that one in y2. I would go adjust my window so I can see it fairly nicely. You know, you don't need to go out to 10 on the x-axis. Maybe go from 0 to 3 by 1s. Y-axis maybe go from 0 to 5 by 1s just to kind of overshoot the given graph, and you'll get a nice picture. The first question says, find the sum of the areas of R and S. So I need both of their areas. So for part A, first thing I'm going to do is region R, and I'm going to color because this is area. So it's all about the rectangle. It's all about top function minus bottom function. I'm going to integrate from 0 to this intersection. You need to go find that. That's up to you. So you should pause this video and go find that intersection. I'm going to call it A comma B, or actually A comma f of A is fine. It doesn't really matter, but let's call it A. And again, if you want to type it in your home screen and then store it in A, that's fine. Otherwise, make sure you don't round it to anything less than 3 decimal places. So I'm going to integrate from 0 to A. In region R, I'm going to do the top function, which is this one. This is the quartic, so that's g of x, and you don't need to, since they've defined it as g of x, you can use it as such. So you're going to do g of x minus f of x. There's no squaring or anything like that. It's all just two-dimensional, and it's all about that rectangle, dx. Plus, we're going to do region S now. Region S, similarly, gets integrated from A to 2, left to right. Top function is now f of x minus g of x dx. And you'll get points for the integral and for the correct limits, and you'll also get points for the correct answer. Now, the best way to do this on your calculator is just in one fell swoop using your Math 9, and I would draw these in using your VARs, but be careful because remember this one's y2, so you might want to write it above it. This one's y1, this one's y1, this one's y2, and I'm going to leave that one undercooked, and you go finish that off and then restart the video for part B. For part B, the region S, so right over here, let's take a look at S, is the bottom or the base of a solid whose cross section is perpendicular to the x-axis, which is nice. So here's my side length. Our squares, which is my favorite as well. Find the volume of the solid. Well, I'm not whipping it around anything. I'm not making cylinders. I'm simply going to pop figures up off of that base. Those figures are going to be squares. So the cross section is going to be s squared. It's a dx problem. I'm going to go from A to 2. And then I'm going to go replace s. You can't say S, you've got to define what S is. It is this top function, the E function, f of x minus g of x. Or if you define them for College Board as y1 and y2, that's fair also, but it would be y1. But you have to define then. You have to say let y1 equal f of x, y2 equal g of x, but you can do it like that. And then you're going to square it, and then dx. And then again, that can all be done on your calculator, drawing those in under your VARs and your y-VARs. Round it to no fewer than 3 decimal places. And when you bring this up to me to get your worksheet, I should see answers sitting in there. I want you to work your calculator at this point. I'm not working it for you anymore. For part C, let h be the distance between the graphs of f and g. So let h be the distance between the graphs of f and g in region S. So I'm going to define a function, h of x is the distance between these two. So it's going to be top function. So let's go define it. H of x will equal top function, which in this case is the f, or what I have called y1, but I'm just going to call it f of x. bottom function is g of x, right? So the next thing is it says to calculate h prime, the rate at which h changes with respect to x. That would actually be called h prime of x, or you could call it dh dx. But h prime of x, the rate at which it's changing with respect to x, the derivative of a difference is the difference of the derivative, so I can just write it like this, and make sure you write it out because sometimes there's a point given. It'll say student writes h prime as the difference or something like that. And I'm supposed to calculate that rate of change right when x is 1.8. Now let's go take a look here. When x is 1.8, here's what h of x would have been doing. Is calculating the distance between these. It's growing, it's growing, it's growing, it's growing. It reaches a maximum and then it starts to shrink and shrink and shrink and shrink and shrink. So I know that I'm going to get a negative rate of change because that distance is shrinking. How do you do that on your calculator? Easiest thing to do is just do this whole thing under a math 8. So I'm going to write math 8. And you are just going to do the derivative in math 8 of, and you're going to do f of x minus g of x. You can do them separately, but you can just go like this. And again, you can bring those in on your calculator using your y vars option, and you're going to calculate that at x equals 1.8, and it's going to be a negative uncooked, and I want you to fill that in. Last one, next page. This is a 2014 one, so I'm giving you the ones off the previous years. It's pretty standard that you get one of these. It's pretty standard that they're calculator active, and you can see this again is number 2. That's kind of a pattern, not to say that's what you have. Maybe you won't have one at all, or maybe you'll have a non-calculator active one, but they're pretty typical. That's why we're reviewing them. Hello. All right. Number 2 from 2014, again, we've got another quartic function, x to the 4th minus 2.3x cubed plus 4. That's obviously the bottom function. Top function is y equals 4. So there we go. Part A. Find the volume. And again, I'm going to shrink this down again so I have some more working space. So this is really nice for that. Still getting used to this new smartboard, but there are some really good advantages to it. All right, so let's go do this over here. For part A, I'm going to take and whip region R around y equals -2. Revolving solid formula is pi times the integral from 0 to, you calculate it right here. So you're going to go calc intersect right there. And then we do axis to the outer edge, that whole distance, which is top function minus bottom function. It's 4 minus a -2, which is going to be 4 plus 2, or 6 quantity squared. That's capital R. You can see this. This is -2, and that's 4. Capital R is 6. So it's going to be big R squared minus little r squared is the axis to the inner edge of the curve, which again is going to be top function, which is f of x, minus bottom function, minus -2 is plus 2, quantity squared dx. And you're going to go do that. Make sure you remember the pi. Bring this in using your y vars since you'll already have graphed it to get this intersection. And I'm going to leave that one undone. Letter B. Region R is the base of a solid perpendicular to the x-axis. Sweet. Isosceles right triangles. So this is now an isosceles right triangle popping up and out of this screen. It's 1/2 the integral from 0 to that intersection point. Side squared, which would be top function minus bottom function. And you can write it using f of x because they defined it that way. And then that would be top function minus bottom function squared. Don't forget that. It's side squared dx. And again, round 2, no fewer than 3 decimal places. And finally, I was trying to get this in 25 minutes. I had 24, 37. Yeah! All right. x equals k divides this region into two equal pieces. So let's say I'd probably be right about here. That wouldn't be good. There's going to be more to the right. I'm trying to get a decent, maybe right about here. This is the vertical line x equals k, right? But do not solve an equation involving integrals that could be used to find k. Well, if that's in two equal pieces, then this piece has to equal that one. That's all I would do. I'd say the integral from 0 to that k, which I don't know, of top function minus bottom function dx must equal the integral from k to here, question mark, right? Top function minus bottom function dx. That's the easiest one to set up, but you could have also said this, that left piece in area must be equal to, if those are two equal pieces, 1/2 of the whole distance, 0 to question mark. You could do that way too. So either way, I like this one better. That's it. Bring me your notes when you're done, and I will give you a worksheet. Adios, amigos.